session, we are going to talk about continuous probability distribution. We'll be trying to use majority of these continuous probability distributions in R. So the theoretical concept of it, yes, a little bit we would be covering regarding each of these distributions, but the major focus of it talks about the primary application of each of these distributions and what are the kind of R functions that are available to execute these continuous probability distribution. So that would be the typical focus of this session. So agenda wise, we would talk about the different probability distributions that are supported by the base R package, right? The base R, we are not talking about additional packages here. Different probability distributions that are supported by R. We'll spend some time understanding the normal distribution, which is one of the core distributions for a lot of business applications. Then apart from normal distribution, there are a few more distributions that are used in hypothesis testing. When I'm saying hypothesis testing, making inferences from the samples. Taking the sample data, making some kind of inferences to the population. So there are a few important distributions that will come in handy there. So the primary among them, these are the three: the chi-squared distribution, the F distribution, and the student's T distribution. So we would be spending some time understanding each of these three. Then a lot of applications in lot of domains where the data follows different kinds of patterns, and some of the most commonly used patterns again for different kinds of data, one being a gamma distribution. So we'll see how the gamma distribution is different from a normal distribution. So what would be the typical shape of a data which would be following a gamma distribution? Similarly, we would spend some time on exponential distribution, which is otherwise a special case of gamma distribution. We'll talk about it. Then another kind of distribution which my data can follow could be a beta distribution. So we'll try some kind of graphs for all these distributions. How does this distribution typically look like? And similarly, we would be looking at Cauchy distribution. Log normal distribution again has a lot of applications in the real world, especially when I'm working with stock prices and all. I would expect that the stock prices follow a log normal distribution. Then we have some kind of applications related to logistic distribution, Weibull distribution. So these are all univariate distributions, right from gamma distribution to Weibull, along with the ones that are above it. They are all univariate. And we would also try to handle, if at all there are two different variables or two or more variables which are very much interrelated or correlated among them, how do I really handle them? So we will talk about a multivariate normal distribution which has so many applications, because we would be looking at correlations and covariances and various such kind of aspects in the real world. Then a uniform distribution, one of the most simplest of the distribution. So we will look at the uniform distribution. And finally, we would just introduce, if at all my data is not following any of these specific patterns, I want to create my distribution out of the data itself. We are calling it as an empirical cumulative distribution function. So how do we look at all these things is something that we are very much looking at here. Now, so with this, we'll get started with this session. Few important things. All these distributions are nothing but they are the patterns of the data, right? I'm taking the data, I'm looking at a histogram of the data, right? And I'm seeing whether this particular histogram, I can map this histogram to a particular theoretical pattern. And all these distributions are simply the theoretical patterns. So if I can more or less map the histogram of my data to a theoretical pattern, I can proceed for further analysis, right? I can draw a lot of inferences because theoretically I know a lot of things about that particular pattern. So I can make lots and lots of inferences by understanding that my data is following this particular pattern. So that's one of the prime reasons every data that we look at, we try to map it to some kind of a pattern so that the next level analysis, whether it is drawing some kind of conclusions or creating some kind of predictions, all these things become more and more handy once I am able to map my data to a particular pattern. So these patterns, they are available. One, if my variable is discrete, we have different kinds of discrete distributions. And if my variable that I'm talking of is continuous, again we have different kinds of distribution. So again, n number of distributions are being theoretically researched and created as patterns for us, so that every data that we are coming across, we could see which pattern is more closely representing our data. And let me tell you that patterns are more like ready-made templates for us. So if our data is following one of those specific patterns, I can understand the attributes of the data more and more effectively, and that is one of the prime reasons, especially if I have to move towards inferential and predictive kind of analytics. I am observing the existing data, trying to map it to a specific pattern or a specific combination of patterns. It could be one single pattern, or I can map it to a combination of patterns. But once I am able to map it, it means I have generalized my data. The way I am getting my data, I'm moving away from exclusively my data to a very general form of a data. And once my data is general, I know how it will come in the future. From how it has come in the past, I will have an understanding of how it will come in future. And because of that, I can make lots and lots of conclusions. Okay, I can make lots and lots of probabilistic comments. I can make lots and lots of inferences by looking at the distribution that it is following, and lot of decision making becomes more and more simpler. So that is where understanding different kinds of distributions come in more and more handy. Now, coming to R, there are good number of distributions that R supports, both in case of discrete as well as in case of continuous. And let me tell you, this session is not explaining the theoretical aspects of each of the distributions in depth. You can very well refer to my other videos on probability, where each and every distribution and the theoretical base of each of these distributions is dealt in depth. But whereas as far as this session is concerned, we are more focused on R. Probably we'll take a data set, we'll see to what extent each of my data is getting replicated through a particular distribution. If I'm trying to map my data to a particular distribution, how would that distribution look like, right? Now, in R, there are, for every distribution, if you see, there are a good number of distributions that R is supporting. A beta distribution, this is a list of both continuous as well as discrete. Beta is a continuous distribution. Binomial is a discrete distribution. Cauchy is again a continuous. Exponential is continuous. Chi-squared is continuous. F is continuous. Gamma is continuous. Geometric is discrete. Hypergeometric is discrete. Log normal is continuous. logistic is continuous, negative binomial is discrete, normal is continuous, Poisson is discrete, sign rank is discrete, and T is continuous, uniform is both in continuous as well as in discrete, Weibull is continuous, and Wilcoxon rank sum is in the discrete case. So these are different kinds of distributions. In this session I am focusing more on the continuous cases itself, but remember these are the R functions. So if I want to understand the beta distribution, the function is beta. If I want to understand the Cauchy distribution, the function is Cauchy. And these are the parameters that it will take as inputs. So when I am talking of beta distribution, I have to give shape 1 and shape 2 as the inputs. Whereas if I am talking of a Cauchy distribution, I have to give location and scale as the inputs. Similarly, if I am talking of F distribution, I have to give degrees of freedom 1 and degrees of freedom 2 as the input. So these are the various parameters that each of these distributions will take. So it is a quick ready reference reckoner for you. Of course, you can very well search the net as well, or you can very well look out for the help file of R as well to talk about what are the inputs that you have to give to each one of them. But much more than that, a few important things for all these distributions. R gives 4 different kinds of functions. The ones that are prefixed with P, they are called cumulative probability functions, right? Which is talking about the probability of a particular random variable taking on a value less than or equal to X. So these are called as cumulative probability functions. Generally, you will find it as an S-shaped curve. So for any value of X, it talks about the probability of obtaining a sample value that is less than or equal to X. I'll try to find out for each value of X, what is the probability that I'll get a sample value less than or equal to X. That is